Here's a handy table that hopefully you'll have near you if you have to answer questions about who's soluble and who is not. Okay, down the left side here, we have the first part of the chemical formula, and to the right, we have the second part. So for example, let's take the top line. You have aluminum acetate. That would be soluble. Okay, aluminum bromide, also soluble. Aluminum carbonate, it has an asterisk there. That means that doesn't exist in nature. Okay, no such compound. And then you just go across the row, and here, aluminum hydroxide is insoluble. And what else do we have? D, so aluminum sulfide would decompose in water. And what's the other one we need? A slightly soluble. Okay, let's go down to lithium, go across. Lithium carbonate is slightly soluble. So look at this chart for a while and come up with some different compounds and determine whether they're soluble, slightly soluble, insoluble, decomposes in water, or they just don't exist. Note that the S on the chart on the previous slide means the compound is soluble. In a chemical equation, we represent that by aqueous, AQ. That's the symbol for a solid in solution. Insoluble compounds are indicated by the letter I. In a chemical equation, the symbol for a solid that does not dissolve is S. So let's look here. That's aqueous. It's in solution. This is in solution. This is in solution. However, the silver chloride is insoluble, and it's a solid that is also the precipitate. Precipitation reactions are often called either double replacement or double displacement because it looks like the ions switch places with each other. So here's our reaction, and let's look first at sodium chloride. First of all, the bond between the sodium and the chloride breaks, and the sodium, follow this line, comes over here and bonds with the nitrate. At the same time, the bond between the silver and the nitrate breaks, and silver now bonds with the chlorine. Here are a couple examples of precipitation reactions. The first one, we have lead nitrate plus potassium iodide gives us lead iodide, and look at here, that's S, that's the precipitate, and then potassium nitrate. The second one, silver nitrate plus potassium chloride. Here, the precipitate is silver chloride. You can see the S. And here's potassium nitrate over here. We'll get into all the details of why reactions happen later, but note in the reactions above, chemical bonds break and reform to produce solid products, right here, the precipitate. So we're breaking bonds and putting them back together with different partners. Just as important as when a precipitation reaction will occur is when it doesn't. It will not occur if both products, and remember, the things on the right side of the arrow are called the products, over here are the reactants, so it won't occur if both products are water soluble. So if we mix sodium nitrate with magnesium chloride, we think we're going to get sodium chloride and magnesium nitrate. However, both of these are soluble, so they're both aqueous, so we can have no reaction. And you can see the X there, you can see the line through there, so that's just not going to happen. Predict the products of this reaction, potassium phosphate plus magnesium chloride. So take a couple seconds or minutes, and when you're ready, pull out the tab. I'll wait a second here. Okay, let's pull out the tab and see what we have. Let me try and get it snug up there. Okay. Hopefully you recognize this is a double displacement reaction. So the potassium over here is going to break the bond with phosphate and join up with the chlorine. And here we have it, potassium chloride. The magnesium will break up with the chlorine, okay, and go with the phosphate. And that's what we have here, magnesium phosphate. So it's a double displacement precipitation reaction. Predict the products of this reaction, potassium phosphate and magnesium chloride. Well, let's see. We know that the potassium will join up with the chlorine and the magnesium with the phosphate, but we have to make sure we get the right compounds. So potassium has a valence of +1, phosphate is -3, magnesium is +2, and chlorine is -1. You get that off the periodic table or from your past chemistry experience. So let's see, we have potassium joining with the chlorine, okay, and then we have magnesium joining with the phosphate. This is not good yet, but let's check it out. Let's see, potassium is +1, chlorine is -1. All right, so that's good. That's a real compound. Now magnesium and phosphate. Magnesium is +2 and phosphate is -3. So we have to do a crisscross there, and we put 2 down here for magnesium, and nope, we put a 3 down there for magnesium. It didn't crisscross, and we have a 2 for phosphate. Okay, so we have 2 there. All right, so now we've got those balanced. Now we have to figure out, how do we balance this equation? Well, let's start with potassium has 3 over on the left-hand side and only 1 here. So let's try putting a 3 there. See where that gets us. Okay, we now have 3 chlorines. Here we have 2. That's not good. So what can we do there? Well, let's see. Let's go to magnesium. There's 3 magnesiums on the right. So let's put a 3 here in front of this. We now have 6 chlorines. Uh-oh. We only have 3 over here. Well, let's change this to a 6. Okay. And what do we have to do over here on this first one here? We only have 3 potassium. We have 6 there. So let's put a 2 there. Okay, and you know what? I'm going to erase some of this other stuff so you can just see the what we're putting in front. And I think we have a 6 there on the potassium. Kind of wiped out part of potassium. Put a 6 here. Okay. Now let's count everybody again. 6 potassium and 3 magnesiums on both sides. 6 chlorines here, 6 chlorines here. And over here we have 2 phosphates. And here we have 2 phosphates. So I think we've got it balanced. But what did we forget to do on the right side? You have to know that this magnesium phosphate, we're going to put a little S there, that's our precipitate, and potassium, let's see, potassium chloride here is aqueous. Okay, so that would go. Now let's pull this guy out. It probably shows it a little bit neater. And is that what we have? Yep. So please check that answer with your work. Predict the products of this reaction, calcium fluoride plus sodium sulfate. This will be a double displacement reaction, so we're going to figure the calcium will join up with the sulfate after it breaks its bonds, and sodium will join up with the fluorine. So let's see what we have. Yep, sodium fluoride plus calcium sulfate, where here's your precipitate, the calcium sulfate. Predict the products of this reaction, and then put in the phases of the products and balance the equation. So first we need to know the valences of these pieces. So calcium is +2, and we get this off the periodic table. Fluorine is -1. Sodium is +1. Sulfate is -2. So we're predicting a double displacement reaction. So we have calcium joining with sulfate, and we have sodium joining with fluorine. Now let's get the valences here. Calcium is +2, sulfate is +2. Okay, this is good. And we know this is going to be the precipitate, so that's a solid. We put an S down there. Sodium is +1. Fluorine is -1. So that's good. So our compounds are correct. Now let's balance it. On the left side, we have 1 calcium. Okay, so calcium 1 on the left, and it has 1 on the right. Fluorine, we have 2 on the left, 1 on the right. Sodium, 2 on the left, 1 on the right. And sulfate, 1 on each. So really, the only issue here is the sodium fluoride, and lucky for us, it's the same compound we're talking about. So if we just put a 2 there, we're in business. And then the last step, this is aqueous. So we put the little AQ in there, and now we check our work. And yeah, we got it.